Okay. So we're going to be doing problem 18 of the EE301 12-week review packet. Let's get started. So this problem concerns a low-pass RC filter. Now this problem actually just tells you it's a low-pass filter. But in case they told you to determine it on your own, the way you can figure that out is that in a simple RC circuit, it's a low-pass filter if the output is on the capacitor, okay, and it is a high pass filter if the output is on the resistor, okay. So that's something easy to memorize, like I've been saying in the previous questions. Sometimes these things you should just put them on a sheet and then look them over before the exam starts. Obviously, don't look at them while the exam's going, but right before the exam starts, it can be helpful to just have these things memorized and in your brain. That way it's fresh. So let's get started with the problem. The first one is just to determine the cutoff frequency. So the cutoff frequency is the highest frequency at which you're expecting a clean output. After that, the circuit is supposed to cut it off, and that's what makes it a low pass filter. It only allows low frequencies. So we just use the equation on the bottom of your AC equation sheet, which is labeled filters. It's the same for high pass and low pass filters, just 1 over 2 pi RC. So we're gonna say 2 pi R in this case is 4.7 K, and then the capacitor is 500 pico, pico being 10 to the 12th, or negative 12, my apologies. So we do that, and we're going to get roughly 6.773 kilohertz. Remember, this is going to be in hertz or kilohertz or some other metric prefix of hertz. The next step will be to find the gain of the circuit. As you can see here, the equation says to do V out over V in. Got a little bit of help with this actually. Compare that to the maximum value of 1 for a low frequency range. Okay, so the first thing we're going to do is we're going to take that. Obviously, the frequency that we're looking for is 0.1 FC. So that's just going to be 0.1 times that value that we found before. So 6.773 kilohertz, and that's going to be 6.773 kilohertz. Just moving the decimal point over basically. And then the next step we're going to find, so remember that AV equation, AV equals VO over VN. And actually on our equation sheet, if we look, there is an elaboration for that for low pass filters. We have 1 over the square root of R over XC, and we square that minus or plus 1, and then all of that on the bottom is square rooted. I drew it like this with the 1/2 power. It's perfectly acceptable to draw it with the square root sign instead. So one thing we need to find before we finish up and plug everything in is we need to find XC, right? So XC is equal to 1 over 2 pi F, and then the value of the capacitor. So that's 1 over 2 pi, and then we have our 6.773 K times 500 pico, and that's going to give us something like 46.997 kiloohms. Remember, X is in ohms. We're just using the metric prefix killi. So finally, what we're going to do is we're going to plug it all in. We're going to get 1 over R, which is 4.7 K over 46.997 K, and that's going to be squared, plus 1, and then we'll plug that into the calculator. I would highly recommend using the math print mode on your calculator so that you can just kind of type things out as decimals instead of having like a lot of parentheses. It's really easy to make a mistake that way. we're going to get roughly 0.995. Now on the answer key, you're going to see a slightly different version of the equation. It's going to look something like this: xc over radical r squared plus xc squared. That is totally acceptable to use. It is quite literally the same exact equation. It's just simplified, but it is not on your equation sheet. So it's not going to be, so you have to memorize it or derive it yourself just by multiplying by xc squared top and bottom. Xc on top and bottom. I decided to just use the version that's on your equation sheet because I thought it would be a little easier and you don't have to memorize that version. Both are perfectly acceptable. Right now, what we're going to do is we're going to find the voltage gain again at a different value. We're going to find it at 0 or at 10 FC. So to do that, we're going to take frequency, multiply it by 10, and that will get us 677.3 kilohertz. Pretty easy. And then remember, this is FC right here, the cutoff frequency. And then we'll solve for the reactance again. So that's 1 over 2 pi FC, 1 over 2 pi 677.3 K times 500 pico. And that's going to be just 470 roughly. So then we'll just plug it into that equation from before. AV equals 1 over R over XC squared plus 1, and then square rooted 1 over, that's 4.7K over 470 squared plus 1. And that's the 1/2 power. And then that's going to give you an answer of roughly 0.09. Okay. So what does that tell you about your circuit? I mean, obviously this is 10 times the cutoff frequency, so this is well past what the circuit is allowed to pass. And as you can see, the gain is very, very low. So that means when you try to push a value through that is at that, when you try to push a value through that is at that frequency, you're going to get a very small signal, versus the other case where you're going to get, if you're very, very small, because this is a low pass filter, you're going to get a very high, almost 1-to-1 output of your signal, which is going to be good because this gain is pretty close to 1, meaning the entire voltage is being passed to the load. Where this one's very small, meaning almost none of it's getting to the load, and most likely the load wouldn't even turn on at this point if you were supplying it like the minimum voltage or close to the minimum voltage it needed to turn on, which normally you would. And the last part, determine the frequency at which AV is equal to this, or VO over VI is equal to that. So they want you to basically take the problem we did before and do it in the opposite order. So what we're going to do is we're going to start with AO, AV equals 1 over R over XC squared plus 1 square root. And what we're going to do is we're going to plug in all those numbers and we're going to solve for our unknown. In this case, that is XC, unknown. So we plug in all these numbers. We have 0.01. We have 1 over 4.7K. This is squared. And then we'd have XC here plus 1. And we would put that in 1/2. And then what we would do is we'd want to plug it into our calculator using the number solver function. It's probably the simplest way to do it, and to ensure that you don't make a mistake. So you just square root it, or put it in, and you put that in as the x, and it would solve the for that value for you. It should all fit just fine in the calculator. If you'd rather do it by hand, that's totally acceptable. What you do is you would find the reciprocal of both parts. So you would just flip both parts underneath the fraction bar, and then you would square them. Okay, so you would get something like 1 over AV squared equals R squared over XC squared plus 1. And then you would rearrange that. You would subtract by 1 on both sides. Then you would want to square root both sides, and you would want to flip that to the bottom. So you'd have something, you'd end up with something like this. And then at the end, you would flip the position. You would multiply both sides by XC, and you would divide both sides by A. And you would end up with the final value, which is XC equals R over square root of 1 over A squared minus 1. And then you would just plug those values in, and you should get the same answer. Let's see here, 4.7 EE3 square root of 1 over 0.01 squared. And that's going to get you an X value of roughly 47 ohms. Okay. Now, once we have XC, it's pretty trivial. XC equals 1 over 2 pi FC to solve for your frequency, which is what we're looking for, right? We're looking for frequency. So all we do is we plug in all these values, rearrange to solve for F. So F equals 1 over 2 pi XC times C. So that would be 1 over 2 pi 47,500 pico. Remember, pico is 10 to the negative 12. So that's going to give you roughly 6.77 millihertz, which is pretty high. And that is the value for part D, and that is problem 18.